Hello everybody, and welcome to another video on my channel. And today we're going to talk about the harmonic potential field path planning that's presented by me, Ashraf. So first, the table of contents. First, I'm going to give an introduction where I'm going to give a little bit of reminder on the potential field path planning method. Then I'm going to talk about harmonic functions and how they help us solve some of the problems of the classic potential field path planning. Then I'm going to talk about the boundary conditions and how we usually set them in a path planning problem context. I'll then describe a recursive numerical algorithm for computing harmonic potentials on a given map. Then we are going to show some of the caveats or some of the problems with this method and a little bit of modifications that are used to overcome some of these problems. And then finally, I'm going to show the results and the final algorithm. So first, a reminder of potential field path planning. Now, as usual, here we have a setting where we have an autonomous mobile robot or any type of vehicle, and it's trying to reach a goal right here. And the purple solids are actually obstacles. As usual, we have two types of forces: repulsive forces by the obstacles, which push the autonomous vehicle away, and an attractive force by the goal, which tries to attract the autonomous vehicle. At each moment in time, the autonomous vehicle moves under the influence of the total force. And now some of the advantages and disadvantages of the potential field method. So some of the advantages, it's actually really easy to implement and it has low computational complexity. Some of the disadvantages, one of them is grave, is that we might risk of falling into a local minima. And this might happen when at some point on the robot's path, the sum of the repulsive forces and the attractive forces is actually equal to 0, which means that the robot cannot move from this position. Now, this leads that we can sometimes get stuck in these local minima and we just cannot be guaranteed to find the path from the start to the goal. And now we're going to talk about harmonic functions and how we can use them to solve the local minima problem because of some of the characteristics that they possess. So harmonic function f on a domain gamma satisfies the following equation, which we call the Laplace equation. So that's the Laplacian of f, which is the sum of the second order derivatives with respect to all of the coordinates, is equal to 0. Now, one of the most important theorems that give us one of the desirable characteristics of harmonic functions is called the no local extremas theorem. It states that if f is a harmonic function on a certain domain, gamma, then we are sure that f cannot attain any local minima or maxima in the interior of gamma, and it only attains its maximum or minimum value on the boundary of gamma, which we denote by this symbol here. So this means that if we have a certain harmonic function, we cannot have any local minimas inside a certain domain, and we only have saddle points. Now, so a simple intuition for the 2D case would be if we computed the Hessian, the diagonal elements of the Hessian would be the second order derivatives with respect to each of the coordinates. In this case, we have 2. Now, in this case, which is the 2D case, we know that the Hessian is a symmetric matrix, so all the eigenvalues are real. In the case of a harmonic function, we know that the trace of h, which is the sum of the diagonal elements, in this case it's the Laplacian, at this point, is actually equal to 0. So this means that the eigenvalues cannot have the same sign. Okay, so we are sure that we have eigenvalues of different or mixed signs. Okay, so we have one positive, one negative in this case. Now this means that the matrix H cannot be positive definite and cannot be negative definite, which means the point at which H is computed cannot be a local minima or a local maxima. Now we have to talk about the boundary conditions and how we usually set up these boundary conditions in a path planning problem. So let's have these obstacles here. We have triangular obstacle and a circular obstacle. Now the robot needs to go from this start position to this goal position. And let's assume that we have a certain potential U that just influences the workspace of the robot, and the robot must move under its influence. Now also let's assume that U is actually harmonic. So how can we ensure that we have a harmonic function that neatly describes the robot's path from the start to the goal. So, first of all, we have to ensure that the potential has high values on the boundaries of the obstacles. Now, this will ensure that the robot will steer away from these obstacles. But we also want it to be attracted to the goal. And by that, we have to set a low value of u at the goal, actually the lowest value. So this leads to what we call Dirichlet boundary conditions, which is we set u to high values on the boundaries, and we set it to a low value in the goal region. And we set it to some mid value, okay, or we just solve for the potential function, and this will give us a function that has the highest value on the obstacle boundaries and has the lowest value, which is the local minima at the goal, which in this case coincides to the global min. Now, other types of conditions that are usually used, which might be desirable, are called Newman boundary conditions. So this also, in addition to some of these value conditions, it just ensures that the gradient of the potential is tangent to the obstacle surfaces. So this means that the gradient of, or the derivative of u with respect to n is 0, where n is a normal vector to the obstacle boundary. Now, in this video right here, we will just focus on the boundary conditions. We might discuss Newman boundary conditions in a later video. And now we're going to talk about numerical computation and how we can actually devise a recursive algorithm to compute the harmonic potential on a map. So first of all, the first step is that we discretize. So we have these obstacles here in the map, and then we just lay a grid on top of them and divide the workspace into a rectangular grid. It could be uniform, non-uniform. Usually, in this case, we will take it to be uniform. So the step size in the x-axis is equal to that on the y-axis. Now, and we just replace the obstacles with occupancy grids. So we just report if each cell is actually intersected with an obstacle or not. And we just flag that by putting a 1 in the corresponding map matrix. Now we're going to talk about how we actually just compute second order derivatives. So we have this grid right here. This is the value ij. To the right, we have ui plus 1j. To the left, ui minus 1j. Up, we have ij plus 1, and down, ij minus 1. The step size is h in both directions. Now, it can be easily shown that we can numerically approximate the second order derivatives at this point ij using the following equations. In the x direction, we have ui minus 1j plus ui plus 1j minus 2 of the value at this point, all divided by x squared. We can reach a similar argument in the y direction. Now, to enforce the Laplace equation, we have to make sure that the sum of both of these is actually equal to 0. Now, if we just do the little bit of math and reorganizing terms, we can actually get to this equation. That is uij is equal to 1 over 4, the sum of all the values in the 4 neighboring points. This right here would be an update equation that we could use to enforce Laplace's equation. So all of this just leads to an algorithm, numerical algorithm to compute u on a certain map. So first we initialize u according to the obstacle and goal locations by setting the Dirichlet conditions. That is, we just set it to a certain high value, let's say 100 or 1, whatever, and a low at the obstacle boundaries, and just a low value at the goal and a medium value at the interior. Then we just repeat. We just compute the update equation. So at each moment in time, we just use this numerical update equation. Uij is equal to 1 over 4, the sum of the 4 neighbors. And then we just preserve the boundary conditions. So if after the update, some of the obstacle boundary locations or the goal location changed its value, we just reset it back to whatever we just did in at the beginning. So we just set the obstacle boundary to a high value and the goal location to a low one. Or we could just choose not to update at all any value at the boundary of the obstacle or at the goal location. So we just update the interior points. We could just do that. The main important step is just to preserve the boundary conditions. Then we just keep repeating. Now, one might ask how many iterations is actually required? Well, we could think that we could do just like 100, 100,000, who knows? But the main idea is that we're trying to approximate Laplace's equation. We're trying to enforce it on U. So U started with a certain initialization. We're trying to ensure that U is actually approaching a harmonic function. So what we do is that we just stop when the maximum value of the norm of the Laplacian. So at each step, we approximate the Laplacian on this grid function U. We take the maximum value and we just keep monitoring this value as we iterate through this update. So we might reach a step where the numerical round of errors would cause us to start increasing the maximum value of the Laplacian. And when that starts increasing, we should just stop the iterations because we are simply getting away and further away from a harmonic function characteristic. And this was actually quite evident in practice because as I was reiterating through a certain U matrix, I just noticed that the maximum value of the norm of the Laplacians just started increasing after a certain step, and I just had to stop there. And now some of the caveats and modifications that we could do. Now we actually might ask ourselves, did we just solve path planning? Because we now have a potential function that attains a global minimum at the goal, has high values on the boundaries. We know it does not have any local minimums that the robot can get stuck at in the interior. So by just following this potential function, we could get to the goal, right? Well, sadly, not quite. Now, some of the reasons of why we just did not exactly solve path planning. Well, first, the theorem that we used, the no local extrema, is actually a theoretical result. So it applies to real harmonic functions with the harmonic function satisfying exactly the Laplace equation. And we knew that using a numerical computation algorithm, we only can get a function that is like approximately harmonic. So it just does not exactly satisfy the Laplace equation, but it just approaches it. Second, the quality of the solution actually depends on what numerical algorithm we used. Now, in the previous slides, I just used a really vanilla, quite simple numerical algorithm, which has a really simple update. Now, we might have certain algorithms that perform better and might lead us to a better quality of solution because it helps us converge to a more harmonic function, but I'll just leave that to another time. Now, third point, which is really quite important, is that even though we have just created this harmonic function, we still have no guarantee of how this would look like or how the potential surface would look like. We still don't know how easy it is to navigate through these surfaces. So we might have a lot of flat regions, which is probably quite characteristic of using the Dirichlet conditions. And these flat regions will be really hard to navigate because of the small numerical inaccuracies. Because if we're searching for a downward direction of U, we will have a hard time finding it because of the really close U values. And fourth, and most importantly, we still have saddle points. So the saddle points, we might get actually drawn to a saddle point, and we just have to navigate our way out of those. But saddle points are really quite easier because we are sure that we have a direction in which the potential just in which we will be able to move again towards the goal. So saddle points are quite easier than others. So some of the modifications that we could do now, we could just start with doing something I call a local search. So when I reach a point with really low potential and I just get stuck there and I do not have a way to move around and also decrease the potential, then I just initiate a search around the current point to look for another point with a lower potential that has a collision-free path. So I just test some of the points in the neighborhood to see if I can reach them without hitting the obstacles, and if they also have a lower potential than mine, and then I just move to those. And by that, I'll be able to navigate out of the local area that I'm just stuck in at the moment. Now, it might be that sometimes the local search just fails, and I'll just have to look for another point that is sufficiently far from where I am, but that does not cause a really sharp increase in the potential value. So in this case, I will be taking a step uphill just for the sake of getting rid of this local minimum trap. And I'll just look for a point that does not cause a really huge increase in potential that is actually also sufficiently far. And we'll just describe what we mean by that in when we describe the full algorithm. Now, the results and the final algorithm, we're going to put everything together and devise a full harmonic potential field algorithm. So first, we just find nu numerically, and we initialize the position of the robot. Then we just keep repeating. So at each point, we just move in the negative gradient of the potential function. So at each point, I just compute the gradient using the neighboring cells of the current cell, and I just move in that direction. Now we just check if this motion actually caused an increased potential or not. So if it does not, then we're good, and we just go back and repeat the step. But if it did, that means that I have to start doing the local search. And that means that I'm currently stuck in kind of a local minimum. Not exactly, it's kind of like a numerical problem. And I just have to start doing a local search. Now in the local search, we just increase the neighborhood size until we just can't. So I start at the current point, I increase the neighborhood, let's say a 3 by 3 neighborhood. I just look around. Do I find a point with lower potential? If I don't, I just go a step further, 4 by 4, 5 by 5, until I just hit the boundary of the map. And if that succeeds, then I just go back and repeat the step again, because I'll be able to get rid of this kind of local minima trap. Now, if this fails, as we know, we need to look for a point of least increase. So we are going to move uphill on the potential field surface, but we're going also to choose a point that's not sufficiently close to our point, because if we did, for example, let's say at a certain point IG, I just move to one of the direct neighbors of IG, which has a least increase. Then if I did that, in the next step, I will just go back and get stuck in IG because I'll move in the downhill direction. So that wouldn't really help in getting rid of those. So one possible idea is that I'll search in the neighborhood of my current point. I find a point that minimizes the ascent or the increase in U plus 1 over d. D is the distance between this point and my current point. So this 1 over d term just forces the function to look further away from the current point, and also take into account that I do not want to increase the potential value that much. And then when this finishes, I just return and do the same iterations again and again. So now we're going to apply this algorithm to this type of map. We can see here that the start is here, the goal position is here. Now we can see that this map has many obstacles and could be quite challenging for a classical potential field algorithm and possibly any path planning algorithm, because navigating these tight corners will not be an easy task. So let's see how our harmonic path planning just does. So this right here shows the path that we were able to find using the harmonic potential field path planning. You can see that the robot can easily navigate here in a kind of smooth path. Now here it seems to have been stuck in a local minima and just was able to find a straight line leading to a point with a lower potential and better characteristics. And again, it might have been stuck here, around here, another straight line, and probably here, another straight line, and then just glided towards the goal. Now, this local search idea works just fine until we get to a neighborhood of the goal, in which we are kind of ensured that we will be able to reach the goal safely. So some of the final thoughts and future ideas that we could do to enhance this harmonic potential field problem, or maybe just look at other variants of it. So we could just try other numerical algorithms. As I said, to compute the potential, there is probably other iterative solvers like the Gauss-Seidel, let's say the SOR, all these types of numerical solvers that could be used in solving the systems of linear equations recursively. We could also look into the idea of using multi-resolution grids because, when we are trying to use this harmonic potential method on let's say, a robot arm, for example, or a robot manipulator. Now, this robot manipulator, let's let it be, for example, 6 degrees of freedom. I'll have to apply the harmonic potential field on a 6-dimensional space, for example, and this would lead to an extremely large number of grid points. If we were using a uniform grid, we could look into some of the ideas of multi-resolution grids in which the resolution of the grid just depends on whether it's close to an obstacle or not. So we just refine the map really well, close to the obstacles, and just leave it having, just large cell sizes away when where we do not have actually obstacles. Now, this could lead to a lower computational complexity because we will have less and less cells, and the increase in the cell number would not be that exponential when we increase the dimension. But now that would lead to a more difficult idea of how we approximate the gradients or even the Hessian, because that would require some other types of algorithms to compute those. We could also test the Newman boundary conditions, which I heard could actually help a lot in the flat region problem that might have been one of the reasons the Dirichlet method was actually quite tough to converge. The Newman boundary conditions would ensure that the robot's path would be tangential to the obstacle surfaces, which would lead probably to a better path. We'd also, one of the most interesting ideas that I've recently seen is that we could consider the uncertainty in the obstacle locations by having, for example, a certain, let's say, probability distribution of the map. So in each cell, we have probability of it being an obstacle. And we could just devise some harmonic potential fields that take that explicitly into account. And we call those gamma harmonic potential fields. And they're actually quite an interesting idea. I might take a look into it in some future videos. And that's it. Thank you very much, everybody. Thank you for listening, and thank you for watching my videos. And I'd very much appreciate if you just leave me a like, or if you have any ideas or comments that you'd like me to try. I'm more than open to receive your feedback on the videos. If I could just do anything better in the presentations. If you want me to discuss some sites more, maybe discuss more of the code, or any part of these ideas, you're more than welcome to just leave your comment in the comment section. And yeah, thank you very much.